Alright, let's take a look at a couple example problems for these mass spring damper systems. I'm just going to cover setting up the problems because they come down to second order constant coefficient ODE and we are experts in solving those. When you solve these problems for the homework, I'm fine if you use Maple to solve the actual ODE, but know that solving constant coefficient ODEs is definitely material that will be covered on an exam. I expect you to know how to do that by hand. But for these application problems, if you want, you can go ahead and solve them using Maple. So in this first example problem, we're giving information about the spring that a force of 400 newtons stretches a spring 2 meters. That's information about the spring constant. We know that a mass of 50 kilograms is attached to the end of the spring, and it's initially released from the equilibrium position with an upward velocity of 10 meters per second, and that the medium offers no damping. So what do we know? We know that the medium offers no damping, so the damping coefficient is 0. We know that the mass is 50 kilograms, m is 50. We know that a force of 400 newtons stretches a spring 2 meters. So we know that our K is 400 newtons over 2 meters, so that's 200. So that gives us our ODE, 50, y double prime. Oh, that's 50, not a 5. Plus 200y equals 0. We know that the object is initially released from the equilibrium position. Since y is displacement from equilibrium position, we're saying there's no initial displacement, so y of 0 is 0. And an upward velocity of 10 meters per second. Y prime at time 0, remember up would be negative, so that's negative 10. And that's it. That is the initial value problem that you would want to solve. Okay, in this next problem, we have a mass weighing 8 pounds is attached to a spring whose constant is 4 pounds per foot. It's known that an object traveling through the medium at 1 foot per second will experience 2 pounds of resistance. The mass is initially released from a point 1 foot above the equilibrium position with a downward velocity of 8 feet per second. So let's see. Initially released 1 foot above the equilibrium position. Y of 0 is negative 1. Downward velocity of 8 feet per second. Y prime at 0 is 8. A mass weighing 8 pounds. If you follow the book, we're using the English unit of slug for mass. Okay? To convert from pounds to slugs, you divide by 32. So our m is 8 over 32, which is 1/4 of a slug. We know the spring constant is 4 pounds per foot. Okay? And it's known that an object traveling through the medium at 1 foot per second will experience 2 pounds of resistance. Now remember that we're modeling the resistance from the medium as the resistance, R, is your damping coefficient times the velocity. So we know that the resistance is 2 pounds. That's a constant times the velocity of 1. So that means that our spring constant is 1. So we have the ODE 1/4 y double prime plus y prime. That's a lie. The spring constant is 2. Plus, and the spring constant is 4y equals 0, and you have your initial conditions, and you're ready to go. Take a look at one more. You have a 1 kilogram mass attached to a spring. 32 newtons of force will stretch the spring 2 meters, and an object moving through the medium experiences 20 newtons of resistance if it's traveling at 2 meters per second. Find the equation of motion. So let's see, we have our mass is 1. 32 newtons of force will stretch the spring 2 meters, so we know that our spring constant is 32 newtons over 2 meters, so that's 16. We know that 20 newtons of resistance is our damping coefficient times 2 meters per second, so our C is 10, and we're left with y double prime plus 10y prime plus 16y equals 0. I didn't give you initial conditions, so you couldn't go any farther than this. You could get me a general solution to that equation. There is no initial value problem, so that's it. Okay, that's that.